Hey everyone, welcome into this lecture on planes in space. In the last lecture, we derived formulas for lines in space, and in this lecture, I'd like to derive a formula for a plane in space. So let's start by first trying to sketch a plane in space. And it's going to look something like this. And so, as we talked about when we derived the equations of lines, it requires to identify a line in space, it requires 2 points. So to identify a plane in space is going to require more than 2 points. It's going to require 3 points. So I'm just going to pick 3, and by the way, they have to be 3 non-collinear points. They can't all be in the same line, so I couldn't pick this one. Wouldn't be good enough. I need like maybe this one, right? All right, and so I want to try to describe or find an equation for this plane here, which I'm going to name capital pi. So the reason I'm naming this capital pi is because probably we're going to want to name these points P, Q, and R. All right, and so we need to somehow, by the way, this plane is somewhere in space, just kind of, we need coordinate axes somewhere. They don't have to be close by, but it's somewhere in space. So here's our X, Y, Z coordinate axes. And there we go. So we want to try to describe this plane, right? So what are we going to do? Well, we need, number one, to know the direction of the plane in some sense, and that might sound weird. But a plane is a two-dimensional object living in three-dimensional space. So what that means is that it takes up all but one dimension of the space, right? And the one dimension of space has to be described, or can be described, by a vector that is orthogonal to the plane, or perpendicular to the plane. So to get this vector, what we can do, and we'll do this in the future. Right now I'm just going to write down one way to do it. But what we can do is we can make, out of our 3 non-collinear points, we can make 2 vectors. And you can pick these however you want. I'm going to pick them so that they're at P, just for the sake of the picture. All right? But we've got our vectors PQ and PR. And we want to find, using these 2 vectors, we want to find another vector that is perpendicular to our plane. Well, the plane contains both vectors PR and PQ. It contains both of them, right? So if we take the cross product of these 2, then the resulting vector will, automatically, just by definition, right, be perpendicular to both of them, and therefore it'll be perpendicular to the plane pi itself. So this green vector here, n, this is going to be what we call the normal vector to the plane. It's not in the direction of the plane, it's in the direction that is not in the plane. All right, but that's the best way to describe our plane, actually. So n here is the normal vector. It's a normal vector to the plane pi. All right, and just based on the way we set this up, for us here, we might need this later. We're not going to worry about how we built it in this case. We're just going to always assume we have it. But yeah, we need it though, right? So one way to get it is to take the cross product. So the way I've taken the cross product here is take the vector PR crossed with PQ, where PQ and R are all points in the plane. Okay, so there's our normal vector. By the way, once we have it, it's going to be a vector with 3 components, and so we're going to give this vector, call the components of this vector A, B, and C. So this vector gives us the direction of the plane, right? In some sense, it gives us the one direction that's not in the plane, and so therefore we know the direction that the plane is in, the directions that the plane spans. But the problem is that this vector can be picked up and moved all over the place, right? It's not good enough. We also know that we have this vector P, right? So kind of similar to how we did with the line, we can think of connecting a position vector here, call it R, or call it R naught actually, R naught, to the point P, all right? And so this is just going to be the vector OP from wherever your origin is to the point P. And at this point, we're going to use this vector and one other one. So the next thing we want to do is we want to be able to describe any point, right? So what about this point here? This is a generic point in the plane. Let's call this one P prime, just for the sake of lack of creativity. But this point is going to be our generic point. So it's got variable coordinates, X, Y, Z. And this one you want to think of being able to move all around the plane. I'm going to move all of it, including, so you want to be able to move this all around the plane, and we want to have an equation which will tell us that no matter where we move this point P prime, right, wherever we move this point P prime, it'll be in the plane still. All right, and so the way we're going to do it is just like we did with the line. We are going to make a vector All right, we're going to make a vector that connects to this. Call this vector r. So there's our vector r. And we're going to try to describe something in terms of r here, right? But the problem is r does not live in our plane. Just like r did not live on our line in the last lecture, right? But what does live in our plane is the vector that connects p to p prime, right? And because of the way we built this, what's got to be true about this vector p prime and our normal vector n? Well, if p prime lives in the plane, then if you dot that with n, dotted with n, right? If you dot that with n, then what should the result be? Well, it's got to be perpendicular, so the dot product better be 0. So let's write down a couple things. By the way, this magenta vector here connects tip to tip of our vector r and our vector r naught, and so this vector right here can be written as a difference. So this one is r minus r naught. You could rearrange that if you want. All right, and so our defining property of the plane. This is our defining property of the plane. All right, is that our position vector, r minus r naught, so this vector of the point in the plane connected to the generic point, dotted dot product with n has to equal 0. This is our defining property. Okay, so we're going to work this out. Now to do it, we need coordinates for our point P, and just like we had with the line, we're going to call the coordinates for this x naught, y naught, z naught. There's our initial point. Okay, and so by the way, that means then that r naught is the vector with the same coordinates, because these vectors r and r naught are in standard position, and r is of course just x, y, z. All right, our job at this point, we're pretty much done. We've done all the theoretical nonsense. Our job is just to compute this, to write this out in terms of all the things that we've described here. So we've got that, we've got that, we've got that. We want to use all three of these things to write out an equation of our plane. And we can do it. All right, so r minus r naught, this is going to be vector. We can just do the subtraction. We know what we're doing by now, right? So it's component by component. So x minus x naught in the first component, y minus y naught in the second, z minus z naught in the third. And then we need to dot this with n, right? So r minus r naught dotted with n is going to be this vector, x minus x naught, y minus y naught, z minus z naught, dotted with a, b, c. This should equal 0, right? And what we end up with then, if we multiply this all out, is we get a times x minus x naught. Remember, dot product is component by component, add them up. Component by component, right? So plus b times y minus y naught plus c times z minus z naught equals 0. There you go. There's an equation of the plane that passes through the point x naught, y naught, z naught, and has direction vector, normal vector. Let's just call it the normal vector. Call it by its true name, right? Normal vector a, b, c. But we can do better, and the book is going to want this slightly differently. So you can distribute all this out. X naught, y naught, z naught, those are all numbers. Z, x, y, those are variables, right? And so if we distribute this out, we can rearrange it to write it as ax plus by plus cz minus can get factored out, right? Ax naught plus by naught plus cz naught equals 0. All right, and then what you'll find in the book, and this is a little bit annoying, okay, but it's just the way it is, but what you'll find in our text is that this number, including the minus sign, is called plus d. All right, and so the equation of a line becomes ax plus by plus cz plus d equals 0. So there's the equation of our plane. We've lost a lot of information there, right? Because a, b, c, that's our normal vector. So this is the equation of the plane with normal vector equal to a, b, c. And then d here, d, by looking at this formula, notice that this looks like a dot product of the normal vector n, with, we can tell exactly what it's with, right? With r naught, and it's all negative, so it's actually exactly this term, minus n dot r naught, or r naught dot n. All right, and so d is equal to minus n dotted with r naught, where r naught is your initial point on the plane. And so if you take this all together, then you have all the information you need about the plane.